Hi everyone. Okay, welcome back to another data analysis video. Still sticking with the kind of classical statistical tests and analyses, what we'd often describe as frequentist statistical tests. So in this video, what I'm going to do is demonstrate how to use Python and the various software libraries available to conduct chi-square tests. I'm going to cover quite a bit, so I'll probably split this over 3 separate videos. But in this first video, what I'm going to focus on is chi-square goodness of test fits. And then in the second video, I'll focus on tests of independence. The third video, I'll kind of demonstrate tests of independence using kind of a real data set, and also what you can do in terms of post hoc tests once you have, if you find you've got a significant chi-square test statistic. So chi-square tests, as just a quick recap, are tests that deal with categorical data, and they're based on the counts, frequencies, variable counts, and not the actual value of whatever the variable is being measured. So it's the number of occurrences of a particular variable, or levels of a different variable. And the first one I'm going to focus on is what's known as the chi-squared goodness of fit test. So the chi-square goodness of fit test is kind of like an analog of the one sample t-test. What it does is it tests to see whether this distribution of sample categories match some sort of expected distribution. So for example, you could use the chi-square goodness of fit test to assess whether the demographics of a particular sample, such as a school, a town, a region, differ or match that of the general population. So do the demographics of the population in terms of age, maybe, or in terms of ethnicity of a certain region, are they similar to or not significantly different from the population as a whole, or do they differ? Okay, so that's kind of the example that I'll look at with this goodness of fit test, and I'm gonna kind of manually code it and then show how to calculate this using scipy as well, which is obviously using the scipy software library is obviously much easier. So I'm going to start with the kind of standard software library imports that we'll probably need. I'm going to import NumPy as NP, and import pandas as PD, and I'm going to import the stats library from scipy. So I'm going to import scipy.stats as stats. I'm going to give them those kind of common nicknames. So if I run that first cell, that will do those imports for us. And then I'm going to generate some made up data for the demographics of a county compared to the rest of the UK. Okay. And that's what we're going to do here. We're going to kind of work out the ethnic demographics, say, made up data, completely made up, nationally for the UK, and then we'll kind of look at a particular region. I've just picked Yorkshire because it's my home county, and we'll look at the demographics of Yorkshire in terms of ethnicity, and we'll look to see whether the distribution, the proportions of different ethnic groups differs significantly for Yorkshire compared to the UK on this kind of made up set of data. We actually have the real data for this. There probably is census data on this, but I'm kind of just highlighting how I'm using generated simulated data to kind of demonstrate this analysis. So first of all, what I'm going to do is create a data frame for kind of proportions nationally, and I've selected just kind of 5, we could roughly call them sort of labels for ethnic groups: white, Mediterranean, North African, Mediterranean region, black, Asian, and other. And I've multiplied each of those categories by a certain value. So I've multiplied white by 100,000 there, Mediterranean by 60,000, black by 50,000, Asian by 15,000, and other by 35,000. So those values will give us our proportions. And then I've created for Yorkshire a kind of smaller sample there, 600 times white, 300 times Mediterranean, 250 times black, 75 times Asian, 150 times other. And I've kind of done this deliberately too. So we'll probably find we've got that the proportions for the sample differ from the national kind of proportions, so to speak. And what I'm going to do is with these first two objects, national and Yorkshire, they're just data frame objects, essentially, using the pandas pd.dataframe method. And then I'm going to use the pandas crosstab method. So for the national, I'm going to basically create a new object called national underscore table. I'm going to use pandas pd.crosstab. In parentheses, I'm using the index. I'm saying as the index, use national, which was this object we created here. I'm specifying bracket 0, which just tells it to use index by the columns, essentially, the columns of the national data frame, which will, the rows of the national data frame, which will be each of our ethnic groups, essentially. And the columns are going to specify the counts. I'm going to then do the same for Yorkshire using this other Yorkshire object. So York's table, same sort of thing, pandas.crosstab. We're going to use the Yorkshire data frame rows as our index and counts as our columns. And then these last couple of statements here are just print statements. I'm going to print the national table and the Yorkshire table. So this is essentially, let me run that and we'll see what it looks like. This is essentially a breakdown of ethnicity of voters nationally, say, and in the county of Yorkshire. So maybe we're looking at that, voters, the ethnicity of voters, or maybe just the population share. So the question we would be addressing with the goodness of fit table here is, are the counts distributions across categories the same for Yorkshire as the national population? And you can see the output that we've generated here are basically two arrays. And you will notice that these figures here, Asian 15,000, black 50,000, white 100,000, that type of thing, they kind of match what was specified here. And the same for the Yorkshire sample, Asian 75, black 250. If you look, though, roughly the same sort of thing. Okay. So what we're going to do is do a chi-square test now to see if goodness of fitness, to see if these proportions here for our sample differ from these proportions here national. Okay, so the chi-squared analysis based on chi-square statistic, and this is calculated by basically chi-square is going to be equal to the observed minus the expected value counts squared, and then we're going to divide by the expected count. So observed would be the actual number of counts we've observed for each group, for each category. The expected would be the number we would have expected, or the proportion, I guess, the counts with the number of counts we would have expected. So as I've just said there, observed is the observed for each category, expected is the expected count based on the distribution of the population for the corresponding category. So here's a manual way using Python to calculate the chi-squared test statistic for this data set. Okay, so what I'm going to do is I'm going to use the Yorkshire table, which is our sample, as our observed data, yeah, and we're gonna basically use our national table to get the population ratios. So we know what the values are based on, this is supposedly the whole population. It's obviously very small, but we basically want to know what proportion, 15,000 of this total here, what proportion is that, for Asian or white, etc. Okay. So I'm going to create this new object here called national underscore ratio. So I'm just going to take that national table there, the counts in that national table, which is right here, and we're going to divide by the length. So how many observations there are in total. That to give us the proportion of each group in that table, and then just going to print out those national ratios. And then for the expected, what I'm going to do is to work those out to get the expected count. I'm going to create a new object called expected counts. And we're going to take those national ratios and we're going to multiply them by the length of our Yorkshire sample. So I'm not exactly sure how many, but whatever this totals to, the 75 plus 250 plus 300. That is essentially the length of that Yorkshire sample that we've got there. And then you can see the most important line, I guess, really is this one here, which is the chi-square statistic. And then the way that's calculated is as I've kind of specified it up here, it's the observed minus the expected squared, and then we're going to divide by the expected. And I've got to use this dot sum method at the end. Okay, because it's a one-dimensional array, so we're just going to use that once. You'll see I will have to use it twice when we do a test of independence where we've got two categorical variables. But yeah, so observed is this object we've created here using that Yorkshire table. Expected is this object we created here, which is the national ratios times the length of Yorkshire. You can see it's kind of simplifies it. I could have just put all that essentially in place of expected, but it would be a lot messier. And this double asterisk 2 is basically how you specify you want to raise something to a certain power using Python. If it was just an asterisk, it would just multiply. But what we're saying here is what's in parentheses here, observed minus expected, we're going to square it. Okay, and then we're just going to print out. I put print this dotted line as well, just so we can see the difference. But if I run this, it gives us a couple of things. It prints out the national table, or the national ratio. So what we now know is, so if we look at the national table above there, 15,000 Asian voters, members of the population, and that equates to about 5% of the population. Okay. So that's that first print statement there. It's just printed out this table we're looking at here. Then we've got this dotted line which I've printed here just to separate the two, and then underneath I've printed the chi-square statistic, and the chi-square statistic is 18.19 if we round this to two places here. So that's our chi-square value for this particular data. So to know whether that is a chi-square statistic of 18.19 is statistically significant, we have to compare it to some sort of critical value based on the chi-square distribution. So the chi-square distribution is a family of distributions, and it kind of changes shape with the number of degrees of freedom you have and stuff like that. And another thing to also know is kind of a lesson that people are always taught essentially when they learn chi-square, when they're like doing undergraduate stats, is the test assumes that the expected counts are 5 or more in 80% of the cells, and no cell should have an expected count of less than 1, otherwise it's not going to work properly. But we can use the scipy library to calculate our critical value and the p-value for this particular test we've just done above. So we've got our chi-square value there, but what we're interested in knowing is it significant? So what we need is a critical value. That's a chi-square value for a data frame with 4 degrees of freedom. Okay, essentially that's a critical value for a data frame with 4 degrees of the size of ours with 4 degrees of freedom. And what we do is we compare our chi-square value to that critical value, and if it's larger than it, then it's going to be significant at least at the p is 0.05 level. And we also would like an exact p-value, I guess, for our particular test here. So I'm going to use scipy to calculate the critical value and the p-value in this case. So what I'm going to do is I'm going to use a 95% confidence level, and I'm going to use this percentage point function method from scipy stats for the critical value, and for the p-value I'm going to use the CDF, cumulative distribution function, from also a useful method that's available as in scipy. So what I'm doing is I'm creating some objects here. The first one's crit for the critical value, and I'm to obtain the critical value. I'm going to use stats.chi-squared.ppf percentage point function, and then I'm passing in as arguments. I'm passing in quantiles and the degrees of freedom for our particular data set or problem that we're looking at. So the quantiles are 0.95. So we want critical value 95% constant confidence intervals effectively. And in this case, the degrees of freedom is kind of the number of categories minus 1. And we can usually we'd kind of we'd want to split our. We'd probably want a strict quantile on this. Because we'd split the, if we were making a two-tailed test, we'd kind of split the significance level across the two tails of like a normal distribution. But in this case, we're making it's a one-tailed test. We're just comparing one sample against a population distribution. Okay, so our degrees of freedom is 4. We've got these 1, 2, 3, 4, 5 categories, so we're going to -1, that's 4. Number of categories -1 gives us our degrees of freedom, and we're using Q equals 0.95, so a quantile of 95%. Okay, and all I'm going to do here is print out the critical value. I'm actually going to print using a string saying critical value, and then I'll print this object crit, the value that it returns. And then underneath that, we're going to work out the p-value. And to do that, what we're going to do is 1 minus, so the cumulative distribution function shows us as, it allows us to see for a given value the percentage or that fall below a certain value, the percentage of scores that would account for say a 95% confidence interval, that type of thing, and it sums to 1 essentially. The whole thing sums to 1 over a cumulative distribution function. So if we do 1 minus stats.chi-square.cdf cumulative distribution function, and then what we're going to do is for our x value we're going to pass in, so that would be like our x-axis value, chi-squared stat, so what we're doing is passing in this 18.19 that we got for our chi-squared statistic for our particular data set, and specify the degrees of freedom as well. If I run this cell, what you'll see is we have a critical value of 9.49 if we round that to 2 decimal places, and we have a p-value of 0.001 that relates to our particular chi-square statistic. So what this is telling us is if we have a chi-square statistic that's more than 9.49, it's going to be statistically significant. And we know that is the case because our chi-square statistic was 18.19. And the p-value actually associated with it, that's obviously much bigger than the critical value, and the p-value associated with that is the one we've calculated here using this stats.chi-square.cdf, 1 minus that, so it's the complement of that essentially. And that tells us that the p-value is 0.001. Okay, so since our chi-square statistic exceeds the critical value, we can reject the null hypothesis that the two distributions are the same, and accept the alternative hypothesis that they're different. So what this essentially means for our data is the distribution of ethnic groups in terms of population in Yorkshire differs from the distribution nationally. Okay, so that was the question we were looking at with this goodness of fit test. Are the proportions in our sample, are they significantly different from the population proportions, essentially, or counts, we might say. All right, and what we found here, we have a chi-square value of 18.19, associated p-value of 0.001, and that by kind of a long way that exceeds the critical value. So we've got a statistically significant result. Okay, so let's one last thing. So all of that I did there, calculating that manually, that seems like a lot of work. I mean, we created data, but in terms of working out the chi-square statistic manually, and then kind of working out the critical value, and then working out the p-value, um, we can do the same thing. We can carry out the chi-square goodness of fit test kind of automatically without all that coding using the scipy function, scipy.stats.chi-square. So that's what I'm doing here in this cell, and what you'll see is, so what I'm going to do, I'm calling stats.chi-square, and then passing in fobs, which is the observed counts, and fx, which is the expected count. So, and what I'm passing in is observed and expected, and these are our arrays of observed and expected counts that we worked out here. So observed is the Yorkshire table, expected was like that national ratios times the length of the Yorkshire table. Those are the two arguments that I'm going to pass in as our observed and expected counts. If I run that, what you find is we get a chi-square test statistic of 18.19, if we round that to two places, as we got above, and we get the exact same p-value, 0.001. Okay, so those results agree with the results of the chi-square test we conducted manually, but that's obviously much easier to just use this scipy.stats chi-square method to do it. So, but I wanted to demonstrate really how you can calculate this manually, and also how you can save yourself a lot of time using stats and the actual chi-square method that's available there for calculating that. But you obviously have to have the information available to pass in as the observed and expected counts. That's generally going to be quite easy to work out if you've got some sort of table of data that you're interested in. Okay, so that's the end of this particular video. I'm gonna, in the next video, what I'll do is I will demonstrate how to conduct a chi-square test of independence. And then after that, the third video after that, I will do the same sort of thing, but also show how to work out what to do when if you get a significant result, what post hoc tests will help you interpret what that result means. Okay, thank you.